Hey guys, today we're doing Chapter 10, Section 8 of our FST book, which is on confidence and cautions in statistical reasoning. So looking at our notes here, the first thing right off the bat, we're just going to talk about some questions, okay? But before I want to actually talk about how to answer some of these questions, I think it would be best if we just read some of the stuff from the textbook to make sure that we're understanding what's going on. So I am on page 681 of my textbook under the heading Confidence Intervals. And it says the interval 434 is less than or equal to mu is less than or equal to 446 is called the 68% confidence interval for the population mean mu. The quantity plus or minus 6 is called the margin of error for the confidence interval. Confidence intervals were invented in 1937 by Jerzy Neyman, a Polish mathematician who moved to the United States where he was professor of mathematics for many years at the University of California at Berkeley. Statisticians have invented techniques for finding confidence intervals for many different parameters based on various assumptions. But all confidence intervals share two properties. 1. There is an interval of possible values constructed from the sample data. 2. And a confidence level which gives the probability that the method produces an interval which contains the true value of the parameter. The user chooses the confidence level, a percent near 1. Usually, it is at least 90%, and 95% and 99% are also commonly used. A 95% level for mu indicates that 95% of the sample means will fall about 2 standard deviations from the population mean. For this situation, between 440 minus 2 times 6 equals 428 and 440 plus 2 times 6 equals 452. So what they did there was, because 6 was our standard deviation, if we want to fall within 2 standard deviations of the mean, that means that 2 standard deviations would be 12, because it's 2 times 6. So they subtracted 12 and they added 12 to the mean to find their interval. You can report with 95% confidence that the mean score of the population of seniors in Ohio on the SAT-M is between 428 and 452. Compare this result with the one found earlier. A 68% confidence interval for the mean is 434 less than or equal to mu less than or equal to 446. Notice that, except for rounding, each interval is centered on x bar equals 440, which is the sample mean. So looking at that picture on the page, you can see that no matter what your confidence interval is, it's always centered around the mean because you're always subtracting from the mean and adding to the mean to find your confidence interval. Because we're talking about how many standard deviations we are from the mean, which means that the mean is the center of our distribution. Also, as the level of confidence increases, so does the width of the confidence interval. This is because if you want to place a higher probability on your estimate, you need a wider estimate to cover your bases. Okay, so the larger your confidence interval is, the larger your range of values is going to be that could fall within the confidence interval. What does this mean if you would like a finer tuning or a closer estimate of the mean? You have two choices. You can choose a lower confidence level, or you can use a larger sample. Generally, people who use statistics do not want to use a confidence level below 90%, so in order to get within the desired margin of error, they must increase the sample size. Okay, and that's what we're going to do. We're going to make sure that we have the proper sample size so that we never have to go below. Alright, so now we're going to go through and we're going to actually do the notes. So the first problem says, assume we have the problem from page 680 in which our distribution is approximately normal with our mu sub x bar is approximately mu, and which is 440, so that's according to our central limit theorem. And our sigma x bar, which is approximately sigma over the square root of n, make sure you write that into your notes because I didn't add that, and that's approximately 6. Okay, so we want to find the interval in which the sample means are within 1 standard deviation from our population mean. That's our 68% confidence interval. We can say that in about 68% of random samples of size 400 from the population of seniors, the mean will fall within this interval. Okay, so I want it to be within 1 standard deviation from the mean. They tell me that my mean is 440, and they tell me that my standard deviation is 6. So if I subtract 6 from 440, I get 334. And if I add 6 to 440, I get 446. So that is what my confidence interval is going to be for the specific data set, as long as I'm doing within one standard deviation, which is a 68% confidence interval. So a standard deviation in this case was 6. I want within one standard deviation, so I just added and subtracted 6 from my mean. Easy peasy. Okay, next up it says, what is the margin of error for this interval? Well, what I was doing was I was adding and subtracting 6, so my margin of error is plus or minus 6. Okay, next up. Now we want to find the interval in which the sample means are within 2 standard deviations from the mean. That's the 95% confidence interval. So we can say that in about 95% of random samples of size 400 from the population of seniors, the mean will fall within this interval. So if one standard deviation was 6, that means 2 standard deviations is 12. So what I'm going to do is I'm going to take that mean, which was 440, and I'm going to add or subtract 12 from it, which is my margin of error. So if I subtract 12, I get 328. If I add 428. And then if I add 12, I get 452. So if I want a 95% confidence interval, I'm going between 428 and 452, with my margin of error being plus or minus 12. All right, next up, I want 3 standard deviations from the mean. That's my 99.7% confidence interval. Okay, so we can say that in about 99.7% of random samples of size 400 from the population of seniors, the mean will fall within this interval. So if one standard deviation was 6, that means that 3 standard deviations is 18. So basically what I'm doing is adding and subtracting 18 from my mean, which was 440. So if I subtract 18 from 440, I get 422. And if I add it, I get 458. So that's going to be my range of values that are within 3 standard deviations from the mean. Now let's talk about how large a sample is necessary for this. So you're working for a political candidate who's asked you to do a poll of potential voters that you would be accurate to within 3% with 98% confidence. How many voters should you poll, assuming that your standard deviation is 0.5? Okay, well this is a little bit more tricky. So first of all, we need to think about our confidence interval. So from what we're going to do, we're going to look at this table here. Okay, if I know that I need a 98% confidence interval, what that means is that from here to here, I need 98% of my values to fall within that interval. Okay, but remember that the way that my table reads is it does this and everything less. So technically what I'm looking for on my table, because this is 1% and this is 1%, on my table I'm looking for 0.99. So what I'm going to do is go through the center here and I'm going to find 0.99, and according to my table, that's at approximately 2.06. No. That's at 2.32. Okay. So So what that means is this number is 2.32 and this number is negative 2.32. Okay? So knowing that, now I also know that this is my margin of error within 3%. So I can say that mu minus, x bar minus my mu is 3%, which is 0.03. Okay? So now I know that my z-score is my x bar minus mu over my sigma x bar, which is actually just x bar minus mu over sigma over the square root of n. Okay, so what I'm trying to do is figure out how big that n needs to be. Well, I know that this part is just 0.03, so this is 0.03 over my sigma was 0.5. So now I've got that, and I know that according to this, my z value should be 2.32 or more. So now I'm going to solve this. And in order to solve this, I'm going to start by multiplying by this. Okay, because if I multiply both sides by it, then it'll cancel. Alright, so now I've got 0.03 equals, if I take 2.32 times 0.5, I get 1.16 over the square root of n. Okay? So now, if I want to get this by itself, I'm going to multiply this by the square root of n, multiply this by the square root of n. Okay, that cancels. Now I have 1.16 equals 0.03 times this. So now I'm going to divide by 0.03. So I take 1.16 divided by 0.03, and I get the square root of n equals 38 2/3, or 38.666 repeating. So now what I'm going to do is square that so that I can get n by itself, and that gives me n equals 1495.11 repeating. So that's how big of a sample size I need in order for all of this to remain true at the 98% confidence interval. All right, moving on. Here are just some standard confidence intervals, just so you're aware. If we want a 99% confidence interval, that's at 2.57. And again, the way that I did that on the last problem, to find that 98% confidence interval, you can just do that for all these problems. You don't have to memorize these. So you can always just refer to your table. If you have a 99%, then you know that it's centered, 99's in the middle, which means 0.5% is on either side. So you're actually looking for 0.995 on the table, and you're just looking for what z value corresponds to that. Okay, so 99 is 2.57, 95 is 1.96, or approximately 2, 90% 1.65, and 68% that's 1. So these are just some stuff so that you can remember. You don't have to memorize them though, you can always find them. Alright, let's do a problem. So a research team studying the dietary habits of American adult females charts the daily sodium intake of 100 randomly selected women over the course of 2 months. For their sample group, they find the daily sodium intake to have a mean of 2.850 milligrams with a standard deviation of 450 milligrams. Because the sample size is large, the researchers feel the standard deviation of the sample represents the standard deviation of the entire population of American women. What should the research team report as the 95% confidence interval for the mean daily sodium intake of American women? So we're asking, what is that interval for at the 95% confidence level? Well, let's start by just thinking about some of these numbers here. First of all, they tell me that I have 100 randomly selected women. So that means that my N equals 100. Okay? My sample mean was given to me as 2,850 milligrams. And my sample standard deviation was given to me as 450 milligrams. So, I also know that I want the 95% confidence interval. And looking above, I know that that means that Z equals 1.96. Alright, so knowing that my sample standard deviation is 450, in order to find my sigma x bar, I just need to take sigma divided by the square root of n. So that's 450 divided by the square root of 100, which is 450 divided by 10. So that gives me 45. So then I can take 45 times 1.92, which gives me 88.2, and that tells me my margin of error. So now I'm going to add and subtract that from my mean. So if I take 2850 plus 88.2 and 2850 minus 88.2, that's going to give me my confidence interval of approximately 2,762 to 2,938. Alright, now let's move on to the last part of our problem. So if the research team that wanted to report the mean sodium intake with a 95% confidence interval of 36 milligrams, what should their sample size have been? Well, if I want a confidence interval of 36 milligrams, that means that my margin of error is going to be plus or minus 18, because that's half of my entire interval. So this is my margin of error, which I know is going to be the absolute value of x bar minus mu. So when I'm calculating my z-score, which I know was 1.96 because I'm continuing with the 95% confidence interval, I know that I have the absolute value of x bar minus mu over my sigma over square root of n. So this is 18 over sigma over square root of n. So when I calculate that, I can plug in my 450 here because my sigma hasn't changed. So I have 1.96 equals 18 over 450 divided by the square root of n. Then I can rewrite that as 1.96 equals 18 square root of n over 450. If I just cross multiply and solve this, I've got 1.96 times 450 gives me 882, and that's equal to 18 times the square root of n. If I divide both sides by 18, that gives me the square root of n is equal to 49. So if I square each of those, that gives me n equals 2,401. So if I had a sample size of 2,401 people, then I'd be able to have that 36 milligram confidence interval at my 95% confidence level. And that is everything for section 8.